Okay. Oh, wait. Okay. Wait. Let's get started. So yeah, this Thursday we'll have a midterm, and today will be midterm review. So before I go through this review material I prepared, anyone has any specific question about the things in midterm? Okay. If not, this will be okay. I missed it. Okay. And yeah, okay, let's try to go through, and this will be posted to either later today. So yeah, let's go through this review. So first is notations. So hopefully you are all very familiar with this now, but once again, those three matrices are our favorite poly matrices. We see them a lot. So poly X, if you write in matrix form, is 0, 1, 1, 0. Poly Y, I should be big letter Y, is 0 minus I 0, and the poly Z is 1, 0, 0 minus Y. They are all single cubic gates, and we see X and Z more because they are real, so it's easier to do computation. And they are also written as sigma X, sigma Y, and sigma Z. And it should be capital later. Okay, and also a matrix that's very similar or very closely related to the polys is this Hedema matrix H. And in the matrix form, is 1 over square root 2 and times 1, 1, 1 minus 1. So only here you have a minus 1. Otherwise it's all plus 1. Okay. So it's cool that we know it's matrix form, but usually we use it as a transition between x basis and z basis. So remember there are these, so the eigenvectors of z is obviously 0 and 1, so a vector with 1 here, and so like, remember 0 equal to 1, 0, and 1 equal to 0, 1. And there are the eigenvectors of z, and the eigenvectors of x are those plus and minus. The plus is 1, 1 times square root 2, 1 over square root 2, and the minus is 1 minus 1 times 1 over square root 2. And back to Hedema. So Hedema do this transformation between 0, 1 and plus minus. So if you multiply 0 with Hedema, then you get plus. You multiply 1 with Hedema, you get a minus. And you can also transform them back. So you multiply plus with Hedema, get back to 0, and multiply minus with Hedema back into 1. So it's, yeah, so those two relationship is very cool. And also in general, Hedema square root 2 identity. And as we said, 0 and 1 are the eigenvectors of z and x. And 0, 1 are vectors of z with eigenvalue plus 1 and minus 1. And plus and minus are eigenvectors of x with eigenvalue 1 and minus 1. Question so far? No? Okay. So those are the police and Hedema. And also, we define this dagger notation. That's complex conjugate. Complex conjugate and transpose. And if you do it on vector, so it will turn a column vector to row vector. But also you also do a complex conjugate. So those will be tested in. So we already have those kind of homework, and there will also be questions like this in your test. So don't forget this minus sign here. Okay, when you do complex, when you do this dagger operation. Okay, and once again this then computational basis, and it's actually not totally rigorous, but for qubit it means the basis with 0 and 1. Okay. So we count the basis from 0, 1, and you can see 0 is 1, 0, and 1 is 0, 1 vector. So it's basically the most natural basis you can think of. And well, if the dimension is larger, then we got into ambiguity about do we want to count from 0 or do we want to count from 1. But basically this is the basis where you just label the vectors with integers. And anyway, so computational basis for 1 qubit in our class is always 0 and 1 basis. And if there are more qubits, then you just use bit string. So you use 0 and 1. So here we have a basic bit string. So you have 0 and 1 on every qubit. So for example, you have 2 qubits, then it's 0, 0, 0, 1, 1, 0, and 1, 1. So 4 of them. And then we have gates. So the more familiar gates here. So C0 look like this. So there is a control qubit and the target qubit is a 2 qubit gate. And it's really control X. So if the first qubit is 0, you do nothing, and if it's 1, then you apply X gate on the second qubit. Then you can have multiple control. For example, you have this control NOT, and you do this NOT gate only if both the first and the second qubit are in 1. Okay. And then there is a control Z, so it's very similar to control X, except that you do a Z gate here, and it's also symmetric, so we just write in this symmetric form. And there is swap gate, so what you do is you swap the upper and the lower qubit. Question so far? No? Okay. So back to the Dirac notation. So already talked a little bit about this. So Dirac notation, we often write our column vectors, we just write our column vectors in this K notation. So yeah, look at this K notation here. It means a column vector. So if the qubit is two-dimensional, then it's something AB. And as we said, okay, and so we have and we will do conjugate transpose with our column vector. So we'll have an associated row vector. So this bra vector. So bra vectors are always row vectors, but if we have a sensing here, then we think this bra is actually the ket vector with dagger. So you want to do transpose and complex conjugate. So this A will actually become A star and the B become A B star. So those two vectors are related to each other by this dagger operation. Okay. So that's the K vector and the associated bra vector. And with this Dirac notation, we can do a whole bunch of matrix operation. So we can think about this bra times ket. So this is actually like an inner product. The result will be a number, a scalar, because it's like an inner product. You are thinking about you multiplying a row vector with the column vector, then it's an inner product and you get a number. And you can also do this ket multiplied by a bra. Then it's like this kind of matrix, so it's like an outer product. So this actually give you a matrix as a result. Then there is this really weird thing you probably didn't see in other linear algebra course. That's this tensor product. So you can have also psi ket tensor with another phi ket. And as we say, so this is a tensor product, and if it's one qubit and one qubit, then this will be actually a four-dimensional vector. So it kind of looks like this, but we don't go into detail. But anyway, this will be a four-dimensional vector, and it's kind of like one vector here and another vector here. And yeah, but it's a vector on the tensor product space. And remember, there are also things like entangled vector in the tensor product space, etc. So we don't have much review on the details of tensor product space. So if you don't remember them, you need to check the old lecture notes. But anyway, here we give some example of Dirac notation calculation. So this outer product matrix. So for example, you have this plus ket and times this minus bra, and then this plus give you 1, 1, and this minus give you 1 minus 1, and both of them square 1 over square root 2 multiply together to give you 1 over 2. And the result will be this 1 over 2 and 1 times 1 minus 1, so we get 1 minus 1 and another 1 minus 1. That's 1 minus 1, 1 minus 1. Okay? And then we can do more exotic calculation. So we have a tensor product, and say we have this tensor product state of 0 tensor 0. Then we multiply it with something that looks like very ill-defined. So it's really a matrix. It's really this weird minus ket tensor identity, and this is doable. And because when we have tensor product things multiplying together, so if this is tensor product, this is tensor product, then what we do is we just resolve this slot by slot. So basically, the first slot will interact with the first slot, and the second slot will interact with the second slot. And so you will have the first slot will have this minus bra multiply with this 0 ket, and this will become number, and then the second slot you just have identity multiplied by 0, and so the result is the first slot of this tensor product, because it becomes number, it just disappears. So you get a vector with a smaller dimension, right? So it was a 2 qubit. So say each of these is a cubic space. So you have a 2 qubit input, 2 qubit input vector, right? 1, 2, and you multiply with this thing because you have this weird processing. Then in the end you get a 1 qubit output, right? Just 1 bit qubit at 0 here. And if you write 0 in matrix notation, once again it is 1, 0 vector. Okay. So this is a funny calculation. And then we have something that maybe a little more practical. Let's say you want to measure this now entangled state. So this is, if you remember, this is a beta 00 state. So it's a EPR pair entangled state. So it's in the details is 00 plus 1, 1 times 1 over square root 2 normalization. And let's say you want to measure this thing. So you want to measure its first qubit in sigma x, right? So sigma x, if you think about its measurement operator, is this projector onto plus and the projector, and the projector onto minus. Okay. So then you want to say, so what are the probability and the post-measurement state when you get this plus result? Then you want to see what happens. You get this plus projector on first qubit. Okay? And so plus projector on first qubit, and you only measure on the first qubit, so what happens on the second qubit, it should be usual tensor identity. Okay? And so if you want to see what happens, you measure first qubit in x, then you want to calculate this subnormalized state, where you project the first qubit onto plus and do nothing on the second qubit. And then we can do the calculation with just linearity. So you multiply this thing on the 0 part, and so now everything is tensor together. So now identity times 0 will just give you 0 back. Then you have this plus projector 18 on 0, and they just resolve parts one by one. So this is plus, you will just leave as plus, but you also have this inner product between plus and 0. And that should give you 1 over square root 2, and then multiply this 1 over square root 2 give you 1 over 2. And so you multiply on this 0, 0, you get this plus tensor 0. And similarly, you have this multiply on the 1, 1, then you get this plus tensor 1. Okay? And now everything is still linear, so you can group things together. So you see both of them have the first qubit being plus, and then the second qubit will be 1 over 2. So it should be 1 over 2, 0 plus 1 over 2, 1, right? And if you want to put it in a little nicer form, then you remember 1 over square root 2, 0 plus 1 is the plus state. So you write that 1 over 2 as 1 over square root 2 times 1 over square root 2. So in the end, you get 1 over square root 2 plus tensor plus. So that's a subnormalized state. But if you want to keep with our measurement analogy, then the probability here, I guess I can stop a little. So what's the measurement probability of getting plus here from seeing this subnormalized state? Anyone want to answer? What's the probability of getting this state? Well, the probability will be the amplitude of this state, which is square. So amplitude here is obviously this 1 over square root 2. So probability will be 1 over square root 2 of 0 squared, so it's 1 over 2. And then the post-measurement state is you normalize all this probability. So the state should be this plus tensor plus. Okay. So this is something that we have told about fundamental, but didn't quite have an example yet. And you can expect this in your midterm. So yeah, get familiar with this kind of calculation. You should have learned the tools to do this. Okay? Question? Okay, if not, then we talk about measurement, and let's do a more detailed review on measurement. And once again, we say there are really 3 forms of measurement that we talk about, and you need to read on context. It should be clear, but when you do a measurement, you first need to think about, are we talking about which kind of measurement formulation? So there are 3 of them. And the first is you measure on orthogonal basis. And also measuring computational basis is one of them. And in this formulation, it's quite easy. You think about there is some orthogonal basis on your Hilbert space, right? And I say the basis elements are those EI. And you will just think about, well, because it's basis, then you can write any vector in terms of linear combination of the basis, right? And then when you measure on this basis, the probability of you will have probability of getting one of the I here. Okay, so so the result will be you get some EI, and the probability will be AI squared, and I should say the post-measurement squared, and the post-measurement state will just be this EI. Okay. And then there is this very physical way of saying we measure some Hermitian operator A. So this is a Hermitian matrix, okay, Hermitian, and that means A dagger equal to A. And because it's Hermitian, then it can be diagonalized into the summation lambda I, and projector onto lambda I, which is lambda I ket times lambda I bra. And it's Hermitian means all those lambda I are real number. Okay. And back to measurement. So what do we, when we do a measurement on some Hermitian operator A, then that's very similar to measuring on orthogonal basis. You are basically measuring the orthogonal basis of those eigenvector lambda I. And you just have a different kind of interpretation. So when you get outcome I, so you will also collapse your state back to this lambda I, but you are thinking this is some physical value. So instead of you get I, you say you get this lambda I. So like you measure your position on lambda I or something. And once again, the probability is this AI, but so if you want to spell it out in more algebraic bracket form, so say you are measuring on some state side, then this AI will be the inner product of lambda I and the psi. So probability will be this inner product square. And you can write this out as psi times psi bra times lambda I ket, then lambda I bra times psi ket. So this is useful because, okay, we'll talk about that later. Yeah, so that's the probability of you get the value lambda I. And then there is this also pretty physical concept that you can calculate the expectation value of A. Okay? And yeah, so this is, this is like a random variable notation. So we write this as the expectation value of A. And the notation is a little unclear because it didn't write psi. But what we mean is we will know some psi that you want to calculate the expectation value on. And anyway, and it's, we have proved that the expectation value will be this kind of inner product of A and psi. So you sandwich A with this bra psi and the ket psi. And as we say, it is the expectation value, and that means, well, it's you could write expectation value in formula is this. So you sum over all the value of measurement outcome lambda I and times the probability pi. Okay. So that's the expectation value. And often you can do the calculation from here and get good results. But okay, so we say this. We talk about this measurement of operator A, like just measuring on orthonormal basis. But actually, there is a catch, and the detail of the catch you should flip back to the lecture note once again. But the catch is basically there can be degeneracy. Okay. So let's say if lambda I, so if there can be some lambda I equal to lambda j, then these formula are all kind of wrong, because because if lambda I equal to lambda j and you can get the outcome, let's say you get lambda j, but it's also lambda I, so is the resulting vector lambda I or lambda j? Or lambda j? And both of them are wrong. What you do is so here you see you have this kind of projector onto lambda I, and what happens is you want to replace the projector of lambda I here to this projector onto the space spanned by both lambda I and lambda j. So this lambda I projector plus lambda j projector. Okay. And the post-measurement state will be this. Let's say this is pi and this is pj. And the post-measurement state will be pi plus pj on your side. Then you can get your probabilities and normalized state, etc. Okay. Oh, I guess I should just say here, right? Okay. So we have been doing okay, I will just talk about it later. And yeah, the last one is this. The last one is this most general measurement. So you can have any set of measurements as your measurement operator. So these are the set of matrices MI. And any set except they need to satisfy this completeness relationship. Okay, completeness. Okay, so summation over ABI here, and MI dagger times MI need to be identity matrix. So I need to check this is true. And okay, so the book has a pretty crazy formula, but here we use this subnormalized state trick. Subnormalized to memorize things a little easier. So basically, you get the ith outcome. You think about your state getting to is mi times psi. Okay. And so this will tell you two things. So first is probability of getting this state is kind of like in the first case, right? First case where the probability is your AI square. And so here the probability is the non-square of this post-measurement state. So this is mi psi and is absolute value square. And you can also write it out as inner product, so like this. And so that's the probability, and also the post-measurement state will be this thing and normalized to norm 1. So it's still mi psi, but divided by its length. So because you want the unit vector. Okay. And so yeah. So we also use the subnormal state trick here. So here we are also thinking this as a subnormal state. So we can also read the probability and the state here. And also here we are using a subnormal state trick. Okay. So any question on doing measurement? There will definitely be more than one question on this in the midterm. So yeah. Make sure you guys are familiar with this stuff. Okay, question. Post measurement stage just EI. Okay. Huh? Yeah. AI. You mean this AI? I mean, yeah, but that's just EI because the post measure. Okay, so if you want to talk about some normal state here, is AI EI, right? And because EI is already unit vector, and so known is this AI. Oh, I see what you mean. Okay, yeah. So it's a little different. So you get a phase. So you get AI divided by AI. No, yeah. So if you want to be very technical. Yeah, but let me just check. So you are saying there is going to be a global phase, but yeah, I think it should be global phase most of the time. Yeah, but it should be global phase most of the time, but I think this is the most safe thing you should do. Yeah, because there might be, I'm not sure, there might be things. Yeah, this is a good question. Yeah, I was thinking about this. But thanks for pointing out. So be very sure you need to do this. So there might be a phase on this AI divided by AI. No. Okay. Any other question? Yeah, this is a good point. So this is about this, but there might be global phase. Okay. If there's question.
Global phase rotation of blocks.
The global phase affects the rotation on block sphere. What do you mean? So they see to each block sphere. So I think you mean position on block sphere. So let's draw a block sphere here because it's going to be useful. Huh? Oh, very phase. Yeah. You will get a global phase, right? But okay, so it's tricky, right? Because if you just have a state and a global phase is, as we say, global phase is not detectable. But so the question is, can you do like some entangled thing and you get a global phase? So I'm not quite sure. Yeah, those are good questions and you think about. Yeah, so yeah, I know there can be berry phase, like if you work on a circle on the block sphere, you get some phase. But so if you just do that, then it's global phase. But you can always do some control thing, right? But if you do measurement, then it's very tricky because berry phase is like a unitary, and so you can keep track of the phase on unitary. But can you do measurement to? I think you actually do, because okay, yeah. So you need to be pretty careful, right? So here the face is actually preserved. So here you think about you do like a projection onto those into plus thing, but if you have like a -1 here, and you also preserve the -1 here. So you can see here this plus, the face on the plus and minus of kind of the 0 and the 1 is actually important. Because if you keep a -1 here, you actually give like a minus here. Okay. So yeah. So if this is a global state, then global phase doesn't matter. But if this state is entangled to other things, then you need to be careful and keep a track of the phase with this. Yeah. Okay. 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 So that's something. Thanks for catching up. And okay, we should have time. Okay, more review. So back to review and police. And as the first I say, the police are very important. Once again, x equal to sigma x, also called sigma x, and y also called sigma y, and z also called sigma z. And they have some properties. So the first is the anti-commute. And I don't want to write too much, but basically all the x, y, z anti-commute each other. So for example, xy equal to -yx, just when you switch the order of rotate, the multiplication. And the polys are very cool because their eigenvalues are +1 and -1. And for example, you can easily see from the operator here. So the eigenvalue is this +1 and -1. And okay, now this block sphere is useful here. And we can also have kind of a more generalized poly. So we have this xyz thing, right? Xyz block sphere, and we can also think like an arbitrary direction v. So v is the direction here. And I should probably say anyway. So we can think about a unit vector as some point on the unit ball, right? And so this direction v actually gives will decide another poly vector, and you can calculate it by doing the inner product with this weird sigma vector. And what we mean is actually, so you write v as, so we write v into its coordinate, right? So v is on vx, vy, vz with, well, with non-equal to 1, so like vx squared plus vy squared plus vz squared equal to 1. And so v is this vx, vy, vz, and what we mean by v inner product with the sigma vector is just you have vx times sigma x and plus vy times sigma y plus vz times sigma z. So this is also some 2x2 matrix. It's a linear combination between the polys. And this will also like a poly. So we think about this kind of like corresponding to some direction on the block sphere. This v direction on the block sphere. And yeah. And the thing you need to use most is that, so you prove this in homework, this v direction poly, so v inner product is sigma. You also have eigenvalue +1 and -1. Okay. That's the most important thing you need to remember. And what this means is that, so you can get a whole bunch of property out over here. So like, if you square it, then you will become identity, because +1 squared to 1 and -1 squared also to 1. And if you trace it, it will get 0. So that kind of thing. Okay. Yeah, this is an important thing to remember. Eigenvalue +1 and -1 will be used for a lot of places. So, question? And obviously also this is also important. Yeah. And then we spend a lot of time talking about these density matrices. And well, density matrix, it can be think of them as this ensemble interpretation. So you can think about density matrix rho as representing a probability mixture of pure state. So maybe you have some probability P1 of state side 1 and probability P2 is state side 2. What do I have? Anyway. Okay. And etc. Then the corresponding density matrix will be P1 times this projected onto side 1, and P2 times this projected onto side 2, then P3 side 3 projector, etc. So for example, if you have like 50% being zero state and 52% being plus state, then rho will be 1 over 2, and this 1, 0, 0, 1 plus 1 over 2, and the plus state should be 3. Plus 1 over 2, and plus state should be also 1 over 2, 1, 1, 1, 1. And so the result should be okay, 3, 4, 1, 4, 1, 4, 1, 4, something like this. Okay, and wait. Okay. And if you do time evolutions on U on those density matrix, then the matrix should become U times rho times U dagger. And there is a small trick to remember this, because you are thinking if you have some state side and your evolution under U, it should become U side. Then rho is kind of like this projection onto sides of the ket side and side. And K side become U side, and the broad side should become side U dagger. Okay. And okay, so the rule about evolution is this, and there is a rule about measurement. And so measurement, if it's like a second kind of measurement, you have some operator A, and you want to know the expectation value, then the expectation value has this nice form trace rho A. And but if you want to do some measurement with a set of operator M, then then the post measurement state is so once again the subnormalized state will be just like this U thing. So it should be this MIA and MI dagger. And but the probability here will be, so probability associated with some density matrix is just its trace. And so if you want to get a normalized state, it should be MIA, MI dagger, and divided by the trace of MIA, MI dagger. Okay. And just as we said, all the density matrix need to satisfy those two equations. So its normalization is its trace, so the trace should be equal to 1 if you want to have a proper density matrix. And also the density matrix should also be positive semi-definite, so we write it as is bigger or equal to 0. And I believe we proved it in class that this is if and only if rho is density matrix, right? So rho is density matrix if and only if trace rho equal to 1 and rho is PSD. Question? Okay, so those are density matrix, and obviously there are calculations you have done in homework, and we'll probably also do them in midterm. Then okay, then there are two interesting operations about we are to 310, right? Okay, so we are actually a little slower. Okay, so let's get a little faster. So there are two things, two operations about density matrix that are pretty interesting. So first one is purification. So you have some density matrix on some system A, then you can add another like reference system B and get it to a pure state psi AB. And so you want this row. Sorry, so I should reverse order. So let's talk about the reduced density matrix first. So you have a pure state psi AB. Then you can think about its behavior on state on the system A as just a density matrix array. And what you do is this partial trace operation, trace B. So rho A will be, okay, so rho A will be tracing all the B part of this rho AB. And so actually say rho AB because it is possible for any density matrix rho AB. And if you want to write down in formula, it's like this. So it's summation I and have this I tensor identity on A part and tensor is bra I and then sandwich this identity and ket I. So this is kind of like the operation we do up here, right? So this example is kind of like that, although we do minus state, not computational basis. So that justifies why I want to do this. And also why is this partial trace? Because the total trace, so if we just say if we just have one system, the total trace of the normal trace of this matrix A is just summation I and this IAI. So you only do this IAI on the B part, so it's partial trace. So if you have pure state or any state, you can get reduced density matrix like this. And then this is purification operation where you get a density matrix. Then you say, is there any pure state where you can reduce back to this rho? Then this is actually not unique, but one of the way you can do this is you can do diagonalization of your rho A, and so you have lambda I and project on lambda I. Then your purification is just take square root of you take square root of those lambda I, and you have lambda I tensor some also normal basis I. Okay, we need to be fast. 5 minutes left. Okay, question? No. And okay. Oh, actually, okay. And also those are called streaming coefficients, I believe. Okay. And okay, very fast back, and then let's go to circuits. And circuits, first is this useful calculation tool. You should remember. So when you want to do sigma to n on some computational basis state x, then it will be sum over all computational basis state z, and 1 over 2 to n, and so this is actually n qubit. Okay. And you have inner product between these x and z. So inner product between b string. So yeah, just think of a b string as vector, then you do inner product ma2, sorry. So you have inner product here, x dot z. Okay, so this is a nice formula that I should remember. And then circuits, we don't have much example, but just remember there will be this kind of question where you have some input state, it should must be 0. And you run through a circuit and want to see what's the output state. And also we have this phase kickback technique where we have this quantum oracle UF, and you run some input x here, and you put a recall register into this minus state. Then you will get this cool phase kickback effect where the recall register kind of just stays the same, so it doesn't do anything. And and you will get a -1 phase onto your input register. And I guess we have time, so this is compared to the usual, right? The usual way, it's not usual way, but compared to what happens when you apply this oracle onto standard basis is the x, so input x stay the same, and you will get whatever you input on the recall register, then O plus f of x. Okay, remember this is the definition of your oracle on computational basis state. And you see, so this will give you some weird entanglement between your input and the output, but if you do phase cubic, then there is no entanglement. You just get phased on your input. And also, other thing I just remember is the big O notation. And so I guess the important thing here is remember the treating hierarchy, right? So exponential x is, so the hierarchy we have is like exp x bigger and much bigger than poly x, much bigger than log x. Right? And also something here is like I guess f equal to OG. So big OG, then that means like f is smaller equal to g, and f equal to theta g is like f equal to g, and f equal to omega g is like f lower bounded by g. Yeah. Obviously, this is very sketchy because it's actually defined with all the asymptotic limiting notation, and they want to see a notation, you need to go back, look up the notes. This is just a quick reminder of things. So those are the three big things. Okay, exactly on time. So any question? Otherwise, we'll have a test on Thursday. Okay.